All right, welcome to the screencast for objective number 5. In this, we're going to explain the frequencies of emitted light and how they relate to changes in electron energy. So you're going to see how the location of the electron relates to the frequency of light that we see coming out of the atom. So we're going to do this activity in class. We're going to do flame test where we're going to burn various metal elements and identify the colors emitted. So I'm just going to skip this slide and the next slide, which we are going to watch this video clip together. So a little bit that I need to tell you though, before we do the lab in class, you need to know a little bit about electromagnetic radiation. This is how light travels through space. Sunlight, X-rays, gamma rays, and the video clip up above takes you through all the different types of electromagnetic radiation. Light travels at 3.00 times 10 to the 8th meters per second. That's in a vacuum, so that is the definition of the speed of light. And I have a little electromagnetic radiation diagram that I'm going to give you, so you might just want to leave like 4 or 5 lines in your notes so that way we can put that diagram in there. What we see of the spectrum is only visible light. There are other types of light that you cannot see. So this video clip I'm going to skip because that's the flame test and that's what we're going to do in class. But what I want you to see right here is this is visible light. This is what we can see. So this is the wavelength of visible light that we can actually see. But there are all these other types of light that we don't see at all. This one shows it great because it shows them not having any color to them, like this one does up here, where we just see kind of the Roy G. Biv, the red, orange, yellow, green, blue, indigo, violet. What's nice about this diagram is it shows you also the wavelength. So as you go from red to purple, the wavelength gets shorter. The waves get closer together. The peaks get closer together. And this one just shows it in the opposite way. So this one has more frequency to it. This one has less frequency to it. This one has a longer wavelength. This one has a shorter wavelength. That's going to be very important for our lab as we relate wavelengths and frequencies to the different types of light. So if I were to take the light that comes off of an element when I burn it, and I were to pass it through a prism, these are the line spectrums that it would create. So each of these elements is not giving off all of the different colors. They're not giving off all the reds, all the oranges, all the greens, all the blues, all the purples. They're only giving off certain wavelengths, certain very specific wavelengths. And that's what we see through these line spectrums. And each element is different. So each element has their own signature colors that they emit and their signature line spectrum. So if we were to take the colors from the flame labs and we were to pass them through a prism, this is what we would see. And this is what allows us to identify what elements are present where. So I have a diagram for you to glue in of line spectrums as well. So atoms will radiate light. They will give off light energy, but they have to be in gaseous form to do this. So you expose them to either high temperature or high voltage, and you can get them to radiate light. This light can then be passed through a prism to divide the individual colors. And each element has a unique line spectrum that it produces. So it's a way that you can identify what elements might be present on stars by what colors are coming off of those stars. It can be used to identify elements. So here's a little bit about wavelength. You guys should already know about wavelengths, but again, I have another diagram that you're going to glue in your notebook, this particular diagram, and we're going to label the parts of it, so you might leave a few lines, leave 4 or 5 lines of room. So the parts of a wavelength is the distance between the peaks. Or you could think of it as the distance between the troughs. So going from this trough to this trough is one wavelength, or going from that peak to that peak is one wavelength. Frequency is how many waves pass a point per second. It's how you get different radio stations. You turn into different frequencies in your car. It's how CB radios work. But it's how many of these points pass per second. So if they're closer together, or if they're taller waves or shorter waves, that amplitude is going to have an effect on the frequency. I'm going to show you a video clip on the parts of a wave that'll explain the difference between wavelength and frequency a little bit better. Amplitude is the height of the wave. And then we can also just talk about the speed of the wave, how fast this particular whole wave is traveling through space. But just a little bit about the structure of waves, because a beam of light travels in waves. So we think about light as coming to your eyes as these waves, these individual particles or individual packets that are traveling in a wave pattern. So it's not continuous. That's what I'm trying to say. So a beam of light travels in a wave, but it's actually a stream of tiny individual packets of energy called photons. So as each photon hits your eye, you're perceiving it as a different color because it's traveling at a different speed or frequency or a different wavelength, and that's how you're identifying it. But it's not a continuous beam. It is individual particles called photons. So if it's individual particles, but as we saw on our previous slide, if it's traveling as a wave, if it's individual particles, but it's traveling as a wave, what is light? Is light a particle or is it a wave? Can it be both? Is it both? And this is where you get the dual nature of light. If you're talking about it in terms of photons, then you have to look at it as a particle. If you're talking about it in terms of waves, then you have to look at it as a wave. It just depends upon what you want it to be. In what relation are you talking about it in? So it can be both, and it is both. And I'm going to show you this video clip that's really going to confuse you, but we're going to talk about the dual nature of light. So what's the point in talking about waves and wavelengths and light and all of this stuff when we're supposed to be talking about electrons? So the individual atom is going to absorb energy from the increase in temperature or from voltage, and those electrons will then be excited, or the correct term for it is quantized. What those electrons are going to do is move to higher orbitals. They're going to become excited, and so they can jump further from the nucleus. When those electrons fall back down to their original position, when they're ready to go back to their ground state, they're going to give off energy, but they give off their energy as light. So we can get atoms to emit light. That normal level is the ground state. They jump to an excited state. And different colors of light come from different energies released. So when we go back to, we're in class, we can go back and look at those energy levels. That's where, or the spectrums, that is where those come from. Those individual spectrums that each element produces are those specific electrons that are giving off energy. So we can use this to determine where those electrons are. If they fall a longer distance, they're going to have a different frequency than ones that fall from closer areas or closer to the nucleus. So the electrons are restricted to these discrete principal energy levels, these definite regions. Each energy level is a further distance out from the nucleus. So I'm going to do a Bohr model drawing on the board for you. I don't have a diagram to glue in your notebook, but I am going to give you a Bohr model diagram of this so you can see what I'm talking about when we say an electron absorbs energy and then it falls back down. So there are 7 total energy levels, or 7 total places that we could find electrons at in terms of distance from the nucleus. You can be n equals 1 through n equals 7, and they correspond to the rows on the table. I promise this is all going to make sense to you in the next couple of days. But right now, I just want you to focus on thinking about n equals 1 being the circle that's closer to the nucleus in a Bohr model, and n equals 7 being the one that's further away from the nucleus in a Bohr model, and all the other ones falling in the middle. So n equals 2 is a little further out, n equals 3 would be a little further out, n equals 4 would be a little further out, just all of these circles getting further and further and further out from the nucleus. As n increases, so does the energy the electrons have. So the electrons that are in n equals 4 have more energy than the electrons in n equals 1. So they get further out from the nucleus, but they also have more energy. Now, each of these circles, the n equals 1 area, the n equals 2 area, the n equals 3 area, the n equals 4 area, they all have specific orbitals associated with it. N equals 1 only has 1 orbital. N equals 2 has 2 orbitals that you can find that distance from the nucleus. N equals 3 has 3 orbital types that you can find that distance of n equals 3. And n equals 4 through 7 each have 4 orbital types that you can find that distance from the nucleus. So S, P, D, and F. We are going to create a foldable in class over the differences between an S, P, D, and F. So what I would like for you to do is just listen to me as I talk about this a little bit. S orbital, I will talk about each orbital type, and then we will complete a foldable on it in class to review it. So this information that's on the PowerPoint slide, we're going to put within the foldable. And again, I promise you, you're getting some background information right now, and we will tie all of this stuff together, and it will make perfect sense to you in the next couple of days. So an s orbital is spherical in shape. It is circular. It is the lowest energy level. Don't worry about the rest of this stuff because we're going to talk about it in class. But it can hold 2 electrons. So here's what I mean by n equals 1 is this distance from the nucleus, n equals 2 is a little further out, n equals 3 is a little further out from that. Another orbital type is a p orbital, which is actually 3 suborbitals put together. So all 3 of those put together equals a p. So that is 1 p orbital. They are dumbbell shaped, and the 2p is closer than the 3p, which is closer than the 4p. So they're the same distance. The 2p is the same distance out as the 2s. The 3p is the same distance out as the 3s. The number in front tells you how far it is from the nucleus, and the letter tells you what orbital it's actually in. There are d orbitals, which are 5 of them put together. So you can imagine all 5 of those put together on top of each other. You wouldn't really be able to see much. So that's why they separate it out. And they can hold 10 total electrons. They're 4-leaf clover shape. And the 3d is the same distance out as the 3s and the 3p. So this right here, all 5 of these on top of each other is going to exist in that same space, 3 from the nucleus, that 3n level as the 3s and the 3p. The f's, this is what the f's look like. Now imagine all of those superimposed on top of each other, then on top of d's, then on top of p's, then on top of s's, and you see really quick the electron cloud model is really that. It's a fuzzy boundary cloud. You can't tell what the heck is going on. So there are 7 orbitals together that make one f orbital, holds 14 electrons, and the 4f is going to be, again, the same distance out as the 4s, the 4p, and the 4d. So the 4 tells you the distance out from the nucleus, and the f tells you which actual orbital it's in. So s orbitals have the lowest energy, then p, then d, then f, and they fill in that order. So you fill the s's before you fill the p's, before you fill the d's, before you fill the f's. And you have to also remember that these orbitals are fuzzy boundaries. They're not solid lines like the images you have seen or my drawings that I'm going to do, but we draw them that way just to make it a little bit easier. Each orbital can hold a maximum of 2 electrons, so an s having only 1 orbital can hold 2 electrons. A p having 3 suborbitals can hold 6 electrons. A d can hold 10 total electrons, and an f can hold 14 total electrons. So we're going to watch the video clip in class. We're going to label this on our periodic table, because then again, how does this relate to atoms and being able to tell where electrons are and being able to predict where electrons are located on an atom? We are going to label the s block, the d block, the p block, and the f block in class, and you'll see that an s can hold 2 electrons, and there's 2 there. A p can hold 6 electrons, and there's 1, 2, 3, 4, 5, 6 electrons. A d can hold 10 electrons, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And an f can hold 14 electrons. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons in an f block. So the blocks that we're going to label correspond to the number of electrons each one can hold. And I promise you, when we go to do objective number 6 and we put all of this together, everything about the electron energies, the frequencies of light they give off, or the wavelengths of light they give off, the energy levels, the quantum levels that they're in, and the orbitals will all come together and make sense.